Hello everyone, and welcome to Lecture 6 of our Probability Theory course. Today's topic is repetition of trials and the Bernoulli formula. This is one of the most fundamental concepts in probability, and it will serve as a foundation for many future topics including the binomial distribution and the Poisson approximation. Let me briefly outline what we'll cover today. We'll start with an introduction to repeated trials and why they matter. Then we'll define independent trials and discuss the 4 conditions that must be met for the Bernoulli scheme to apply. After that, I'll derive the Bernoulli formula and walk you through 3 practical examples: a coin toss, a quality control problem, and a classic at least one scenario. We'll also examine the properties of the probability distribution and learn how to find the most probable number of successes. We'll wrap up with a summary of key takeaways. So why do we need repetition in probability? In real life, we rarely base our conclusions on a single experiment. Instead, we repeat the same experiment many times to observe patterns and make reliable predictions. Think about tossing a coin 10 times instead of just once, or testing 100 light bulbs from a production line, or giving a medical test to 50 patients. In all these cases, we're interested in one key question: what is the probability of getting a specific number of successes in a fixed number of trials? That's precisely the question the Bernoulli formula answers. Before we go further, we need a clear definition. Trials are called independent if the outcome of one trial does not affect the outcome of any other trial. A classic example is drawing a card from a deck with replacement. Because you put the card back, the composition of the deck stays the same, so each draw is independent. On the other hand, drawing without replacement creates dependence, because removing a card changes the probabilities for the next draw. In this lecture, we will focus exclusively on independent trials, as they are the foundation of the Bernoulli scheme. The Swiss mathematician Jacob Bernoulli, who lived from 1654 to 1705, developed a classic framework that now bears his name. For the Bernoulli formula to be valid, 4 conditions must be satisfied. First, the number of trials, denoted by n, must be fixed in advance. Second, each trial can have only 2 possible outcomes. We call them success and failure. Success occurs with probability p, and failure with probability q, where q equals 1 minus p. Third, the probability p must remain constant from one trial to the next. It cannot change. And fourth, all trials must be independent. When these 4 conditions hold, we can apply the Bernoulli formula with confidence. Now we arrive at the centerpiece of today's lecture, the Bernoulli formula. It answers the question: what is the probability of obtaining exactly k successes in n independent trials? The formula is p sub n of k equals c sub n to the power of k times p to the power of k times q to the power of n minus k. Let's break down each symbol. N is the total number of trials. K is the number of successes we're interested in. It can range from 0 to n. P is the probability of success on a single trial, and Q is 1 minus P. Finally, C sub n to the power of k is the binomial coefficient, which represents the number of ways to choose which k trials out of n will be successes. This coefficient is calculated as n factorial divided by k factorial times n minus k factorial. But why does this formula work? Let's think about it intuitively. The term p to the power of k represents the probability that k-specific trials all result in success. The term q to the power of n minus k represents the probability that all remaining trials result in failure. But the successes don't have to occur in any particular order. They could be scattered among the trials in many different ways. For example, if we have 3 trials and we want 2 successes, the successes could be in positions 1 and 2, 1 and 3, or 2 and 3. Each of these sequences has the same probability, and the binomial coefficient c sub n to the power of k counts exactly how many such sequences exist. That's why we multiply, to account for all possible arrangements. Let's apply the formula to a concrete example. Suppose we toss a fair coin 5 times. What's the probability of getting exactly 3 heads? Here, n equals 5, k equals 3. Since the coin is fair, the probability of heads, p, is 0.5, and the probability of tails, q, is also 0.5. Plugging into the formula, we get p sub 5 of 3 equals c sub 5 cubed times 0.5 cubed times 0.5 squared. C sub 5 cubed is 10, There are 10 ways to choose which 3 of the 5 tosses are heads, so we have 10 times 0.5 to the 5th power. 0.5 to the 5th is 1/32. 10 divided by 32 equals 0.3125. So the probability of getting exactly 3 heads in 5 tosses is 31.25%. Now let's consider a more practical scenario. A factory produces parts, and the probability that any given part is defective is 0.1. If we randomly select 4 parts for inspection, what's the probability that exactly one of them is defective? In this case, we define success as finding a defective part. So n equals 4, k equals 1, p equals 0.1, and q equals 0.9. Substituting into the formula, p sub 4 of 1 equals c sub 4 to the power of 1 times 0.1 to the first power times 0.9 to the third power. C sub 4 to the power of 1 is 4. 4 times 0.1 is 0.4, and 0.9 cubed is 0.729. Multiplying 0.4 by 0.729 gives 0.2916. So there's a 29.16% chance that exactly one part out of 4 is defective. Now, what if we want the probability of at least one defective part? This is a common type of question. The key insight is to use the complement rule. The event at least one defective is the complement of 0 defectives, so we calculate the probability of 0 defectives and subtract it from 1. For 0 defectives, k equals 0, p sub 4 of 0 equals c sub 4 to the power of 0 times 0.1 to the 0 times 0.9 to the 4th. C sub 4 to the power of 0 is 1, 0.1 to the 0 is 1, and 0.9 to the 4th is 0.6561. So the probability of no defectives is 65.61%. Therefore, the probability of at least one defective is 1 minus 0.6561, which equals 0.3439 or 34.39%. This technique, using the complement, is extremely useful whenever you see phrases like at least or at most. The Bernoulli probabilities have some important properties. First, every probability p sub n of k is non-negative, which makes sense because probabilities can't be negative. Second, and more importantly, if you sum p sub n of k for all possible values of k from 0 to n, the total is exactly 1. Why? Because the sum is equivalent to applying Newton's binomial theorem to the expression p plus q to the power of n. But since q equals 1 minus p, p plus q is just 1, and 1 to any power is 1. So the sum of all probabilities is guaranteed to be 1. This confirms that we're dealing with a valid probability distribution. A very practical question is, which number of successes is most likely to occur? In other words, for which value of k is the probability p sub n of k maximized? There's a simple formula to find this most probable number, which we denote as k0. It satisfies the inequality n plus 1 times p minus 1 is less than or equal to k0, which is less than or equal to n plus 1 times p, and k0 must be an integer. Let's test this with an example. Suppose n equals 10 and p equals 0.5. Then n plus 1 times p is 11 times 0.5, which equals 5.5. So k0 must be between 4.5 and 5.5. The only integer in that range is 5, so in 10 tosses of a fair coin, the most likely number of heads is 5, which matches our intuition perfectly. Let's quickly summarize what we've learned today. The Bernoulli scheme requires a fixed number of trials, a constant probability of success, and independent trials. The Bernoulli formula, p sub n of k equals c sub n to the power of k times p to the power of k times q to the power of n minus k, allows us to calculate the probability of exactly k successes. We can also use the complement rule to handle at least or at most questions efficiently. Finally, the most probable number of successes is approximately n plus 1 times p. These tools are essential for analyzing any situation involving repeated independent trials. That concludes our lecture on the Bernoulli formula. Thank you for your attention. If you have any questions or if anything wasn't clear, please feel free to ask. In our next lecture, we'll explore the Poisson distribution, which provides a useful approximation for rare events. See you then.